All right, here we go. It's an unruly name for an unruly topic, but it's all about sort of programming experience. So today we're talking about the future, and I want to share a programming concept with you that was inspired by the confluence of a few things. Firstly, there's Jason Eisner's Dyna programming language, a sort of prologue with aggregation operators. There's Alexei Radul's propagation networks, in which reactive cells store information about values rather than just values. And most especially, work with analysts using Excel in real time during multi-billion-dollar spectrum auctions. Imagine, if you will, a secure, windowless room in a national capital, locked in with consultants and economists and analysts for about a month. There are no external devices, no internet access except to your auction software, and the job is to help them make sense of what they're seeing, to live code beyond the sum products and pivot tables at which Excel excels. So on these excursions, I'm awed by how efficiently analysts can munge their data, dismayed by the hacks they go through to maintain their spreadsheets, and I'm confounded that despite all my programmer prowess, they can come up with numbers faster. All the same, after a week or so, I have the scripts to tabulate interesting figures for them. Those don't require the same amount of maintenance as the spreadsheets do, and so I spend most of the next month stuck in the room, ruminating over what it all means. This idea is the outcome of my most recent engagement. What can we do to enhance the data-centric reactivity of spreadsheets? Constraint neurologic programming provides a natural bridge. Tables correspond to relations, formulas to rules, pivot tables to aggregators, what-if analysis to parameterization. It's all cute, but then I had an idea that I felt was actually worth sharing. What happens when we treat prologue facts and relations as nodes and edges in a propagation network? By way of example, let's see how this might play out. So in the auction room, we often have measurements of an aggregate phenomena, how the bidders are bidding, and from which we want to infer the contribution of individual factors, like what do they like and why. For illustration, suppose we can measure all the traffic of some sort into a region, but we would really like to find out how much comes from a specific place. Certainly the amount has to be between all and none, and it turns out that provided information about traffic into and out of other regions, we can make some inferences. So suppose we live on a big island divided into regions. We have the north and we have the west. Two facts, basically prologue minus the parentheses in case insensitive. Let's look at these facts differently. Type Control-G to group by region. It's a table just like the inspiration bridge and example tables we've already seen. I typed notes for the introduction so you could see that this tool starts as structured text, kind of like Emacs org mode. The grouped region block is basically the same as prefixing each line with region. Let's see another relation. Traffic data into and out of regions. These facts have associated values, hence the equal sign. Notice that the spacing of this data is tabbed into columns. So now let's pivot this table. Group by the direction of the traffic, group by region. We have a table with column and row headers. The data is the same. The group by command just changes the view, both its appearance and the commands for interacting with it. I present the interface in a text editor not because text is best, though text editors have some advantages, rather because as programmers we're all used to it. I chose the Atom editor because it's fairly easy to instrument. Greater Man would use Emacs. Some of you have made your own. Let's go ahead and name this table. Indenting in this system creates a new scope. By naming the table, we add a prefix to all the relations represented in the table. So now we can ask some questions about our traffic. What do we know about the traffic into the west? Well, the traffic equals 404. To avoid the prefix, we can include traffic facts as example facts. If we change a value, what then? We get a conflict, two values that are at odds. In the future, the equal sign will never be used for assignment. Equals is an assertion that two expressions have the same value. Here we have assigned into west to multiple values, both 404 and 435. To properly override a value, first we should forget what we've already asserted. To forget suggests time and state in order to permit imperative refinement of a model while retaining reactive update. Facts collect from top to bottom. Each assertion is a function from one set of facts to another. A change from one fact may change all the answers to questions below it. In contrast, reevaluating an expression in a Mathematica notebook does not affect related expressions so that the text can get out of sync with the heap of definitions. If you have non-programmer friends who use Mathematica, just ask them about how they work around this fact sometime. To retract and to assert together is to revise. The reduced command merges facts. It normalizes their total effect on the model. It's function composition. Let's reduce again to revise the original. We update into West by patching in place. And what do we know about the West overall? Well, a blank in the question is answered by every unifying substitution. The West is the object of three predicates, region, into, and out of. And if we add another blank, we get all of our facts because they all happen to be predicate-object pairs. Suppose we just want facts involving a direction. Direction defines or unifies with everything that satisfies the direction predicate. However, direction is undefined. So we hit enter again for a quick fix. The system can guess what might be a direction from the predicates that already match an unrestricted blank. There's no magic here, it just requires some context. The trick is having a system where context is readily available. So let's restrict direction properly, and we reproduce the traffic table. Since directions label a column in the traffic table, we can combine them. Likewise, since regions label a row, let's merge again. Okay, we're going to press the key. There it is. So now we have three relations embedded in one table, region, direction, and how their product maps onto values. Now when we modify the traffic table, we assert several facts at once. Notice that new helo facts appear down at the bottom as an answer to our direction question. Let's consider helo specifically. We know that out of helo is a fact, but we don't know its value since we left its corresponding cell blank. To fix the value, let's use a formula. So equals, click, and hit return, just like a spreadsheet. From the formula, the system infers the value of out of helo. Out of helo equals into helo equals 500, so we have a two-link equality chain. If we want to focus on values instead of facts, we ask a different sort of question. And then when the question is fully grounded, here we go, we find familiar functional evaluation. Evaluation is old school. In the future, programmers upgrade to inference. So let's do that. From our data about traffic into and out of regions, we can learn about the traffic going directly from one region to another. Let's see how this could work. The question mark refers to the previous relation. Notice that from to is defined for every pair of regions. Rather than declaring a type restriction, the colon syntax here populates a relation with all the values that match the predicate. Too many in this case. Traffic should only make sense between regions. So to correctly define the from-to relation, we should stipulate that the two regions be distinct. Instead of case, I use underscores to mark variables. At last, we see Prolog's famous turnstile notation. The /tilde says that the two regions should not unify. So read the whole expression formally as the traffic from one region to another both exists and is bounded below by 0 provided the two regions are distinct. Sounds very logic-y. As we did with the grouped and transposed traffic table, we can add some syntactic sugar. I feel this makes for a more natural read. The traffic from one region to another distinct region is bounded below by 0. It's a little bit better. Sifting out the syntactic sugar reveals that the colon syntax is shorthand for a predicate in the body. Surface syntax is a view rotated one way or another. To make these syntax transformations bidirectional, one should retain representational metadata, such as the variable name _s, and the order of arguments to the does not unify operator. So to continue with our analysis, associate the from-to relation with our existing traffic info. The traffic into a region is the sum of all traffic from somewhere into the region. The traffic out of a region is the sum of all traffic from the region to somewhere else. In particular, the traffic into West is the sum of the traffic from the north plus the traffic from helo. Aggregators fold over all unifying substitutions. They remove the need to explicitly construct a set of items to sum over. Moreover, each line actually defines 3 sums, 1 for each region. 3 regions in each of 2 lines makes for 6 linear equations, 6 unknowns. Now, a linear dependency ensures that we won't get a unique solution, and that makes asking about bounds worthwhile in this case. So let's take a look at traffic from Hilo to the west. With Shift-Enter, we can interactively draw inferences instead of having the system do them all automatically. So let's expand into west to see other facts about it. Reduce them to 1 equation. Expand to see more facts. Now we've arrived at the propagation part of our tour. Remember, grounded terms have associated values. Each term is like a slot or cell where you can stick information. Equations relate cells, allowing information to spread from one cell to another. So let's take a look at this chart showing the relationship of into west to other facts. It's equal to 435, and it's the sum of the 2 from blank into west facts. If we learn the value of one of the sum ends, we can infer the value of the other. Propagation goes both ways. Numbers propagate, as do bounds. By propagating the inequality across the sum, we set an upper bound. Since addition is monotonic, a lower bound on one sum end imposes an upper bound on the other. So let's expand to see the derivation. Having found an upper bound for from Hilo to west, can we improve its lower bound too? How is that done? So we're going to copy and paste that and then press space or whatever it is, space to see the derivation. Let's add these facts to our chart. All right. So we'll just make it a little smaller to fit things. So we have the out of Hilo facts, we have the into north facts, and we have the other ones as well. So where does the lower bound of 135 come from? It follows from there being an upper bound on from Hilo to north, which in turn comes from there being a 0 bound on from west to north. What if the traffic into Hilo were different? Let's say 200. So let's scroll up, change one of the entries in our cell, hit return, and everything updates. Not only does the lower bound drop, into west becomes a tight constraint, and into Hilo becomes a loose constraint. So back in the chart, switching into Hilo invalidates the previous inference and updates out of Hilo as well. Our new bound is not as strong, having come around from the other side. Let's ask about both the upper bound and the lower bound at the same time. So here we go. What are the bounds on it? We get a closed interval from 50 to 200. Instead of working backwards, let's see how the 0 bounds might propagate forward. Start by stripping down to the essential relations. So we're going to pull our diagram here to the center. Here we go. Let's add our constraints. There they are. OK, propagate clockwise. Bub, 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 bub. Counterclockwise. Bub, 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 bub. All right, reduce by taking the better bound in each case. There we go. OK, propagate clockwise. Boop, 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 boop. Counterclockwise. Boop, boop. Merge again. And then one more time. Propagate clockwise. Propagate counterclockwise. And that's forward propagation. All right, so let's bring back the editor. All right, so let's try messing with the numbers again. If we changed from 200 to 50, we find that we get equality. And if we go to 49, we have a conflict. The lower bound is higher than the upper bound. To see how these what-if scenarios relate, let's climb up the ladder of abstraction. For our scenario, we're interested in the bounds on from Hilo to west. Include the example module in the body of scenario for unqualified reference. The dot here allows a rule to have local facts. So within this rule, all example facts hold. Let's take a look inside. Here we see the definition of the example table. I use gray in the background to suggest that the original is kept elsewhere. Beyond just viewing the included table, we can customize it. We can override the included version. The original remains unchanged. More importantly, we can parameterize over a term. So let's close up the module and see that we're simply overriding one of the facts. Between an overriding diff and the fully woven version with all customizing patches integrated, some things are easy to see in the derivative and some are clearer in the integral. In the future, we freely switch between the two. Let's try some scenarios. So if we check 500 or 700, we get the bounds. And finally, let's ask about a whole interval at once. The answer is an interval of intervals charted crudely. Dashes for standard intervals, stars for conflicted intervals, and equal sign for singletons. Although we define the scenario with scalars in mind, we can apply it to intervals by mapping the scenario across a selection of values from the interval. Similarly, we can automatically lift other functors, sets, lists, probability distributions, time-varying signals. A generalized propagation network separates the shape of the network from the structure of the data that fills its cells. It offers a new kind of abstraction with more potential than I'm prepared to explore today. Instead, let's just review what we've already explored. All right, being reactive is par for the course in this workshop. For every wibble, have related things wobble. Except we don't actually want every wibble to wobble. While in the middle of typing a question or making a change, a system shouldn't interrupt. Every messenger app seems to experiment with sharing your keystrokes until they realize that people put their thoughts together only wanting to send after they hit return. So in the example, I marked uncommitted changes with a light yellow background. Some questions don't have an immediate answer. It takes time to think things through. We saw this with the Bayes DB stuff earlier, the question of, well, how can we give people the feedback that their system's processing? How long might it take to process? So we should build with these constraints in mind. First and always, keep the interface responsive, process in the background. Report progress, abort if asked, be able to pause a process, inspect it, rewind. This sounds like a list of operating system services. And I'm not sure why the APIs for dealing with processes remain so true to their 1970s roots. I don't think Rob Pike knows either. Perhaps with the web, all the effort has drifted away up into the cloud. Well, that's a topic for another time. And time, speaking of time, it's a funny dimension. It's a good place to keep bugs. Functional programming goes to show that you can get by without time some of the time, and when you do need time, you should be explicit about it. I/O using monads, he says, doesn't look like purely functional programming, and it shouldn't because it isn't. A basic spreadsheet is pure. Every formula is a pure function, but the people who make them are not. We build things over time, and their structure at any moment is just a snapshot. So when I am working with people in an auction room, a lot of their job is to update their spreadsheet when new data comes in because the spreadsheet doesn't do a particularly good job of maintaining its sort of inner constraints. So in order to work with time, we have to step out of time. And I don't mean metaphysically, I just mean that the order of events in a story doesn't need to match the order in which they're written. You can write it backwards. The resolved becomes unresolved, clues skitter away to their hiding places, foreshadows become regular back shadows. When reading, when interpreting, begin at the beginning and go on till the end until you come to the end, then stop. With structured programming, the key idea was to have control flow match code flow. First instruction to first line, last instruction to last line, with some skipped and repeated bits in the middle. Admittedly, this never quite worked out, and I suppose that graphical interfaces are partly to blame because they don't go from beginning to end, they kind of go in a loop. Still, in our example, facts accumulated from top to bottom. A question asked early on ignored spoilers that came later. Time unfolds strung along the vertical. Ask a question twice, you'll get the same answer unless there are new facts in the middle. If we quickly alternate between the two, the effect is to highlight a change. If we have a long list of answers, scrolling from one to the next gives us animation. So analysts know some animator tricks. In our traffic table, we tried several values for into helo, seeing changes in slow motion. In Excel, to make transitions immediate, here's what you do. You start with a sheet, you make a copy, you update some cells, you make another copy, update some cells, and so on. Then you switch between tabs quickly to see your workbook become a flip book. Of course, the copies have no link back to the master, so it's easy to get out of sync. I think there was a mention of cells getting out of sync in an Excel table. So in the example, including a table makes the link, and overriding customizes it. Scope and variables abstracted over it, and then with auto-lifting propagation, we speculated over a range of possible worlds, possible futures. Layer on a user-driven selection function, and then the animation would become interaction. So let's move on to convenient speculation comes from convenient modularity in the example we just indented for new scope. Includes graphed branches, so we get multiple inheritance. How's that for a diamond problem? All right. Excel isn't exactly a tool for dealing with tables. Each sheet is a grid. People may treat part like a table. You can mark a box of cells as a table with sorting and filters, but maintaining the illusion requires diligence. For instance, autofills let you see how each cell refers to others, but they hide the fact that a parameterized formula is being applied to a whole column. Other tools take tables more seriously, but often at the cost of free-form flexibility. Moreover, not all data is tabular. We have trees, too. The example showed trees and tables trying to coexist with a tree understood as a grouped table. So there's more than one way to look at a thing. We've seen many examples grouped by more or less syntactic sugar, expanding an included table. One favorite is the convention of spreadsheet cells. Enter a formula, the sense of what you want, hit return, and see a calculated value, the reference that sense expresses in context. It's like binocular vision. From two slightly offset planar projections, we experience a 3D scene. Any representation that emphasizes some aspect does so by obscuring another. With multiple representations, though, we get to see around the obstacles. All right, last year at Splash, Peter Norvig remarked that mathematical specifications don't naturally translate into C++. There's no surprises here. However, with a good declarative language, the translation can be made even better than the math. At seeing this slide, I was awestruck. Notation practically perfect in every way. Ever since I've been pondering why I reacted so strongly. Earlier, I said that aggregators fold over all unifying substitutions. By listing out those substitutions, we can enumerate all the terms in a family of sums. Unification gives us an unfolded intermediate representation, grouped by the left-hand side to see an expansion of each sum. The beauty comes from having both intentional and extensional views with regular unification serving as the lens in the middle. So an aggregator puts each aggregate at the hub of a network with terms spreading out as spokes. In our example, these spokes joined other hubs, forming a sort of benzene-shaped ring. We propagated numbers and bounds along the network. When Gerald Sussman talked about propagation at Strange Loop in 2011, he propagated derivatives, matrices, voltages. He said, the value here is that I'm allowed to dynamically change the meaning of all my operators, add new things that they can do. One new thing was to have a propagated value track its journey through the network. That's its provenance. I've long used a weak form of this in object-oriented settings. Proxy an object so that all of its methods return a proxy, whose methods all return a proxy, and so on. By the end, you have an image of the data downstream from the original object. This is good for measuring how tangled your system is. These tracer doodads are good for view maintenance, too. You can collect all the metadata necessary to map a view of an object back to its model. Backpropagation makes tracing even better. Given a wrong value, you can trace backwards to find its causes. Sussman went on to say, I can pay a belief in correctness for tremendous flexibility. The problem facing us as computer engineers is not correctness, but evolvability. The whole purpose of thinking things through is to go from a muddled, confused, contradictory idea to a clear, orderly, consistent one. The degree to which our software tools can model confusion matches their usefulness in conceptualizing, brainstorming, and coming to understand things. So a perfect language, one that only compiles correct programs, is a poor fit for a world full of inconsistency and conflict. I'm not exactly saying that we should all be writing Ruby, but a better choice may be a pure language in which chaos is a first-class construct. In the example, some variables had multiple values. Instead of the conventional, non-deterministic OR semantics, I experimented with a sort of over-deterministic AND semantics. So let's take one last look at our example. We'll just scroll up to see what we wrote down here in all of its glory. I like the economy of expression in this. From a table, some equations, and a simple question, we get a nuanced answer. There may indeed be a wide and productive bridge joining logic programming to generalized propagation. And I hope there's another bridge over to probabilistic programming too. But this little demo, I'm not going to say is it. It's more of a curiosity and hopefully a thought-provoking one with qualities that future tools will share, like reactive wibble wobbles, accumulative space is time, speculative possible futures, modular indent and include, tabular trees grouping tables, binocular sense and reference, aggregates that unify unfolds, propagating flexible shape, and conflict that resolves the muddled to the clear. So I'll leave you with 9 criteria against which you can measure your own efforts and the promising ones that you'll hear about in the rest of the day. I'm certainly looking forward to it. Thank you. And now I would love to hear your questions and comments. Yes, please.
Point out to the audience that this is being videoed, and so you can watch it again at a slower speed.
Yeah, so you have to understand, I listen to my podcasts at double time, so I'm just used to talking twice as fast as a normal person. Yeah, you had a question?
Yeah, so constraints and logic, usually there's some pretty tight rules on what you can get away with. And sometimes that's hard for people to understand and work around. So for instance, what's the limits on your arithmetic here that you're able to push inequalities through? Is it like Pressburger arithmetic or some limited form, right?
Yeah, so the question is, how far does this go? And the answer is, I don't know. So the idea with propagation is you sort of, let's throw out completeness and soundness and see what we can get in exchange. So the thing is, you don't need to have a system where you're sure that you've made all the inferences that could be made. It's just useful if your system makes some inferences that you might not have been able to make yourself. And so in the case of a sum, if I have any if I have a sum of 3 things, if I know any 2, I know the third. But if I only know one of them, I still have sort of a plane of possible answers. And there's plenty of things that you probably could infer that you're not going to. But it's the idea is getting something rather than just being left to figure it all out on your own. So that's where I'm sitting on this is, well, when you define a propagator, you're like, well, for any operations, how do we propagate it? And so you say, well, here's the generic way to propagate it, this kind of thing across that sort of thing. And then you can sort of refine it with more strategies of, well, actually, when you've got this, this, and this, you can make a stronger inference than you would otherwise. So one way to think about this may be a little too technical. So like, if you have a monoid, a free monoid, just all the operations make for a bigger string of things that you've combined. And then sometimes, when it's not free, certain parts of it you can say, oh, well, when I have all these things together, they simplify to something simpler. And when I have all these, they simplify to something simpler. So your sort of generalized system is, well, we'll just string together everything that propagated from everyone. And then you have to then say, well, which of these things can now be reduced to something simpler. So that's kind of the approach, generally speaking. I'm ready for another one. Yes?
So, 2 questions. What did you use to make your presentation, and how long did it take?
Okay, so the first question is, what did I use to make my presentation? And the answer is Keynote. How long did it take? I did it on the flight. I came from Shanghai, so it was a long flight. And there you have it. All right.
Philosophically, why are you so wedded to clear?
Why am I wedded to clear?
Conflict, muddled to clear, lower right.
Why am I wedded to clear? Well, I mean, you want to...
You have to resolve to clear. Why can't muddle resolve to useful?
Well, it depends on what your goal is. Clear is good if you want to understand something. Useful is good if it just works, and then you don't have to understand why. And so I'm coming from this, from the context of we have things going on that I want to explain in a super clear way. So I'm doing this for auctions, right? This is where this idea came from. I want to explain this in a super clear way so that a bureaucrat can tell a politician that can tell the press, and then the press doesn't write something that makes no sense compared to where we started. So as we can get that transition through people, that game of telephone as clear as possible, then my job is done. So that's why I'm caring about clear today. Useful wasn't on the agenda. Yes?
Can we play with this anywhere? Is this available?
No, because it doesn't really work very well. This is the future of programming, not the present day of programming. So these are ideas that a system ought to have, not ideas that a system really has down. Like if you were to pay attention to where my cursor goes after every operation, it like just jumps around randomly. I don't even know why. It's not quite right, to say the least. Yes, please.
So how have these ideas informed the code that you do write in the present? Like how can I take some of these thoughts, this notion of propagation, these relations, these transforms, how can I bring this back to, whatever I'm working on?
So, what is, how does this, so how do things relate to the present? There's the question. How does all this relate to the present? Well, what's a good example? Well, I have one. So at the same time that I was working on this and locked in that particular auction room for an unreasonable amount of time, I was also working on a different auction, getting something ready for it. And in that case, I wasn't using Prolog as a DSL to create propagation networks. Instead, I was using Ruby as a DSL to create linear optimization problems. And so I guess the thing to take away from this, sort of the key idea that I had here with the tool was, when can you use a more friendly language as the domain-specific language to generate something that's in a more unruly language? That's what I got out of it. That's practical. So there you have one thing. Yes, please.
How is this different from something like closure for logic with finite domains?
So how is this different from Clojure doing its logic thing that I've looked at very briefly? And I'd say it's not remarkably different. I think it's in the same spirit and grain of things. I wouldn't say a single idea here is novel. I just hope their sort of juxtaposition is kind of fun and cool. I hope it's something to sort of all keep together in a nice 3x3 grid so that you can think about it some more, have a more clear way of thinking of, well, what are all the different pieces and how do they relate? What's the grand unified theory of doing reactivity things? Because there's a lot of stuff that is really in this same grain that a lot of people are doing, I feel.
Okay, let's thank the speaker.
All right, thank you.